All right, so now I will proceed to the last section. So for this last section, I will present the E2W, our TI E2W 72 volt BMS reference design, as well as the 72 volt traction inverter design, designed by our system team. All right, yep. So yeah. Okay, so we do develop a new traction inverter, the battery management system reference design with part number TADA 010247. Okay, so as you can see from the broad diagram there, we actually incorporate two pieces of BQ76972 BMIC to implement this high cell voltage and pack current sensing accuracy, which is as low as plus minus 1.8 millivolt at 25 degrees Celsius and plus minus 25 milliampere at 25 degrees Celsius. So we are using these two chip solution instead of one chip solution is because each chip will handle a smaller voltage range, which is around 60 volt instead of over 100 volt. So this approach will help the system to easy to measure each cell's voltage precisely. Yep. A simple example is when a 0.5 meter ruler is divided into 10 marks, it will be more precise than a 1 meter ruler, which is divided into 10 marks. Because each step or resolution is relatively smaller, so this concept applies to the battery monitor IC as well. And it will improve the voltage accuracy and also the current sensing accuracy. Okay, so the second feature is we also have low power consumption for our system, which is as low as 7 microampere for ship mode and also 20 microampere in normal mode. All right, so this means that our two BMIC in the system are well balanced and does not waste much power during the storage and also the transportation. So this will help us to preserve the battery life for longer use. Okay, and we also have the temperature sensing at each battery cell to sense the temperature. All right. Okay, so now I will proceed to the next slide. This is the board image of our reference board, TIDA 010247. So as you can see, there is a M0 there, MSB M0 G3519. So this M0 is used to collect and also analyze the cell's voltage data, and it is used to communicate with other external submodule, and also is used to convert the data to CAN protocols so that it can be transmitted to other submodule. And our M0 G3519 have 2 ports for the CAN FD, 3 ports for the I2C, and 3 ports for the SPI interface. Okay? Yep. So moving to the second key device is the LM51668P. This is our wide V-in buck converter, which support up to 120 volt from the battery pack. So it will be used to step down the voltage to lower so that it can be used by the internal circuitry of the BMS. And moving down to the third device is the ISO 1640 with the UCC 33420. So this ISO 1640 is the I2C isolator. UCC 33420 is the DC-DC power module. So these two key devices are working together to for the isolation purpose. Okay, sorry. All right. So for the right-hand side, we have the ISO 1042, ISO 1410, and also UCC 33421. So these are all representing isolated CAN transceiver, isolated RS485, and also the DC-DC module, which are used for the isolated communication for the stackable BMS solution. So when there are different ground potentials between every stackable BMS solution, we will use these 3 sockets to enable the signal crossing without the electrical connection. Okay? All right, and the last key devices will be the BQ76972. This is our battery monitor IC, and it can support up to 16 battery cells with plus minus 1.8 millivolt cells voltage accuracy. Okay. All right, so move to the next slide is the detailed block diagram of our TIDA 010247. Okay, so as you can see at the left-hand side, each BMIC, each BQ76972 can support up to 16 battery cells, and the second BMIC will support another 16 battery cells. So it is up to 32 battery cells can be supported. All right, and you can see for the portion here, ISO 1640, this is the I2C isolator. In order to isolate the I2C communication between the first BMIC and the second BMIC. Okay, and we also have the power tree here. This LM51668 is used to step down the high voltage to 5 volt, and then further down to 3.3 volt by using our TPS 7A24. And it will be supplied to the UCC 33410 here in order to supply isolated 3.3 volt to the I2C isolator here. Okay, and another portion is the UCC 33420. This is used to generate the isolated 5 volt bias to power the isolated CAN transceiver and also RS485 transceiver in the system. Okay, yep. All right, so the portion here is the isolated CAN transceiver and also the isolated RS485 used for the stackable BMS unit. Yeah, of course with the temperature sensor here, like 32 temperature sensor is used to monitor the temperature of each battery cells here. Okay. All right. So this is the slide for the software available for this TIDA 010247. So we do release this software in our SDK, MSBM0 SDK, and it is available to download it from online. So, yeah, so the portion here is the available software supported for this reference design. For example, BQ76972 OTP and calibration, working mode transition, and the BMIC I2C API, RS485 CAN read and write API, as well as CAN ID addressing example, and the last one will be the battery data collecting example. Okay, so when I say battery data collecting example, it's something like it can read the 16 cell voltage data and also some protection status flag out from the BQ76972 and the temperature of each battery cells. Okay. All right. So now I will proceed to the key devices used in this BMS reference design. Okay, so yeah, so this BQ76972 is the one pager for the BMIC. So we do support 16 battery cells with enhanced accuracy. So in order to measure the digital current, voltage and temperature data, we use this part use the Coulomb counter algorithm. So what is Coulomb counter algorithm is, it is actually measuring the current through the sun resistor so that it can know the charge flow in and out of the battery. So this algorithm will actually helps to improve the state of charge SOC accuracy during the charging and also the discharging cycles. Besides that, this part is also quite highly integrated. For example, it consists of the high side and fat driver with less than 10 microsecond discharge turn off. And also it contains integrated programmable LDOs. So there are dual integrated LDO inside this BQ76972 with output 1.8 volt to 5.0 volt. So if it requires any output voltage fall under this voltage range, you can actually eliminate the discrete LDO because we have the integrated LDO inside. Okay? Apart from this, we do have the integrated protection features for this BQ76972. So we do have the fuse pin. I think it's quite small there. So there's a fuse pin. It can be used to blow the fuse when there is a high voltage failure occurs. So this fuse pin will help to disconnect the battery pack from being destroyed by the high voltage fault. Okay? All right, so the second key devices is the MSBM0 G3519. So this M0 can support 80 megahertz clock frequency with up to 512 KB flash. All right. So it can support various communication such as UART, SPI, I2C. So, but the thing I want to highlight here is this device is the cheapest MCU in our portfolio, and also can say in the market that can support dual CAN FD controller. So it's a cheaper MCU with dual CAN FD controller. Okay. Yep. So we do offer two versions for these MSBN0351X family devices. If you want to have 512 KB flash, then can choose for G3519. But if you want for 256 KB flash, then you can choose for 3518. Okay. And we do have integrated, ADC inside also with 12-bit, 4 mega sample per second with 11.2 effective number of bits. And we also have the comparator inside. Yeah, and also 8-bit reference DAC and 12-bit DAC as well. Okay. All right, so this is the third devices, the DC-DC module with integrated transformer. So this UCC 33420 can support 5 volt input and 5 volt output with 1.5 watts output power. Okay, so with this integrated transformer, we can support common mode transient immunity above 200 volt per nanosecond with a basic isolation rating such as 3K watt root mean square for isolation voltage, 1.18 kV peak for working voltage, and also 6.5 kilovolt for surge voltage. Yeah, and this is well suited for those power supply applications such as HEV and EV battery management system. Okay, so another thing that I want to highlight here is we do have the EN and also the 4 pin in the IC itself. So we can use it to pull down the device load to minimize the power consumption. And also the 4 pin can be used as output to output the 4 signal to the MCU. Okay. All right, so back to the digital isolator that I discussed this earlier. So ISO 78XX series is our high isolation digital isolator part. So it can support 5.7 kV root mean square for the isolation voltage, 2000 VRMS for the working voltage, and also 12,000 V peak for the surge voltage. And the CMT, the common mode transient immunity is about 100 kV per microsecond. Yeah, and we do support for 100 megabits per second data rate with 11 nanosecond propagation delay. And we do offer 4 channel, 3 channel, 2 channel, and also 1 channels with large creepage such as 14.5 millimeter to meet the IEC reinforced and also the medical equipment requirement and certification. Okay. All right. And another part, this part can support a lower working voltage as compared to the device previously. So this is our mature device, mature digital isolator in our portfolio. And it can support 5,000 V root mean square isolation voltage, 1,500 V root mean square for working voltage, and 10,000 for surge voltage. And the common mode transient immunity is about 150 kV per microsecond. And the data rate is about 50 megabits per second. Okay? So we do offer 6 channel option for these digital isolation family devices. And it is well suited for the applications such as the high EV and also the EV as well. Okay. All right. So yeah, now I would like to proceed to the second section, which is the 72-volt traction inverter block diagram provided by my internal system team. All right. So as you can see, there is a detailed block diagram here. We do have the C2000, the keys devices is C2000, gate driver, half-pitch gate driver, and also isolated current sensor with some of the white V-in bar comparator listed over here. Okay, So the C2000 is indicated by F28P55. So this function is to monitor the real-time motor control and also the motor monitoring. So by running the field-oriented control FOC algorithm, it will help to generate the PWM signals to drive the gate driver for the inverter switches, so the motors can run efficiently by using our F28P55 C2000. Okay, so we also have the half-bridge gate driver with part number UCC27301A. So it will work with the inverter switches to convert the DC voltage from battery to AC for the motor run. Okay, and we have the isolated amplifier for current output as well with the part number AMC0202DR. Yeah, so this is used to sense the DC motor current through the sun resistor, and it will scale the output so that it is usable by the integrated ADC input range of the MCU or of the C2000. Okay, and we do have another device, the programmable logic device (TPLD). So it is used to for the offload. I mean, reduce the load from the C2000. If it helps with the emergency monitoring. So whenever there is a high voltage output or any high voltage alert, it will be going through the comparator, and then the TPLD will provide the output to the GPIO pin of the C2000. Yeah, so C2000 can focus on the motor control application, and the emergency part will be handled by the TPLD side. Okay. All right. So now I will move to the key devices of every key devices in this traction inverter. Okay. So this is the one pager for the isolated amplifier AMC0202D. So I also discussed this device in the earlier session just now. So this is a isolated amplifier with differential output for current sensing. Okay. So the differential output can help to reject the common mode noise built up from the voltage spike while the signal is traveling along the wires. So this will help to ensure the small voltage measurement, like for example the plus minus 50 millivolt, the input voltage range, to be more precise and accurate. And it will achieve a low gain error and also low non-linearity for this case as well, such as plus minus 0.03% for non-linearity, and also gain error is about plus minus 0.2%. Okay? And for this isolated part, for the isolation rating is about 800 V root mean square, working voltage for basic isolation rating, and 1.5 kilovolt root mean square for the reinforced isolation rating. And for the isolation voltage, it will support 3K volt root mean square for basic isolation rating and 5K volt root mean square for reinforced isolation rating. Okay? Yeah. And as mentioned, the differential analog output for this part can support the highest noise immunity, so it can improve the accuracy of the signals. Okay. All right. So proceed to the second key devices is the half-bridge gate driver UCC273X1A. So it can support up to 120 volt with 3.7A source current and also 4.5 ampere sinks current. So the interesting feature of this part is it actually contains the cross conduction protection. So this is a features which prevent both switches to be turned on at the same time. It is kind of like similar to the interlock functionality. Whenever there is both driver outputs are turned high at the same time, the logic circuitry inside the IC will drive both switches to low to prevent the shoot-through current, which might damage the switches. Okay, so this is one of the key features of our half-bridge gate driver. Okay, and we also have the enable pin at the IC itself. It it offers the flexibility for us to disable the gate driver so that we can achieve a low quiescent current consumption when it is not used. So in this case, it is about 7 microampere consumption when the device is disabled. Okay? All right, so yeah, this is the buck converter that is used to step down the 12 volt to 5 volt to be used by the C2000. So for this part, the output voltage range is about 0.6 volt to 7 volt. And we do have two functional mode that we can choose from, the eco and also the FCCM mode. So what is eco mode? It is kind of similar to the pulse frequency modulation mode. So if you choose for this eco mode, it will actually help you to skip some of the switching cycles when the output voltage exceeds certain threshold voltage. But it will continue to switch when output voltage becomes less than certain threshold voltage. So this will help to lower down your switching losses, and at the same time, it will incur another problem. It has a slightly higher output voltage ripples because the inductor current will go to 0 sometimes. So in order to have low output voltage ripple, you can choose for another option, another mode, which is the FCCM mode. So this is known as the forced current conduction mode, in which the device will switch at a fixed frequency, regardless of the threshold and the output voltage. So the inductor current will always carry a certain amount without going to 0. So this will help you to maintain the output voltage ripple instead at a fixed frequency. But of course, it comes with a lesser efficiency in light load condition as compared to the eco mode. Okay? All right. So now comes to the TPLD 1201 in Q1 grade. So this is the programmable logic device that I mentioned just now. So actually you can use, use our TI software such as the Interconnect ICS Studio to implement this combinational or also sequential logic or delay element. So we do offer 2-bit lookup table or 3-bit lookup table and flip-flop, delay, counter, and so on. So whenever, for the lookup table, you can define yourself. For example, for the 2-bit lookup table, 00, you can define it as like AND gate function, 01 is for OR gate, or 10 is for the XNOR gate. So it depends on what is your use case and how you want to implement the logic. So whenever you implement the logic and the diagram, you can send us the diagram, and we can help you to come up with the customized TPLD part, so that it can be used for your system. Okay? So want to add some more is we have the integrated analog comparators and also integrated voltage reference as well. Okay? All right, so now I want to talk about the C2000, the F28P55 series used in the traction inverter just now. So this C2000 contains main core and also core processor, such as the TMU and also the FPU. So TMU, it is known as the trigonometric math unit. It is used to compute for the sine, cos, tangent of the motor phase current. And the core processor, floating point unit FPU, is used to compute for the error adjustment and also the gain for the control signal, so that it can provide the feedback signal and control the PWM signal to drive the motor efficiently. Okay, it will help to compensate the difference between the desired and also the actual motor current. Okay, so both of these core processor and also main core work together to generate the appropriate PWM signal for the motor to run efficiently. Okay, and I also want to highlight that we have the integrated analog solution inside, like 12-bit ADC, we have 5-per, we have the programmable gain amplifier also with 3-per, and also some comparator with the DAC. All right, and it's with the SUB safety rating. Okay. All right. So before I move forward to my last section, anyone has any question regarding the battery management system and also the traction inverter that I shared just now. Yeah, okay. Yeah, so maybe I'll move to the last section. This is the charger reference design. So I will not go through in details for this. So just want to let you know that TI also developed several off-board charger and also on-board charger reference design from 300 watt to 500 watt and up to 3,500 watts. So we do offer several topology for those reference designs, such as full bridge, phase shifted, boost PFC, and also half bridge LLC for those DC-DC stage. Okay. Yeah. So we classify it into off-board charger and also the on-board charger. Yeah. For the on-board charger, we also have solution up to 400 watt. Yeah. I mean the input voltage range is 48 volt. It will be stepped down to 12 volt by using our reference design. So all of the reference design here, we have the readily made physical board. Yeah. So if you're interested, you can later download the slide and then go to our website and look at the reference design and also the schematic and layout inside the link. Okay. All right. So now I would like to show one of the reference design in our portfolio is the 500 watt constant current and constant voltage charger reference design with the part number PMP23464. So later you can just type this reference number in the online. Then you can search for the details of the schematic, layout, and also BOM used in the reference design. Okay. So you can see the key specification here. The topology used is the PFC plus LLC with support to AC input voltage, and output voltage is about 500 watt peak, and it can have the output voltage of about 72 volt or 48 volt with 300 kilohertz resonant frequency. And most importantly, this part can support 96% efficiency at full load. Okay, so when you go through the reference design, you will see the block diagram like this in the website, and also the schematic layout and all the part used in the reference design. Okay. All right, so this is the last slide before I end my session. So this is the 180 watt DC-DC power supply. So it doesn't contain the AC DC stage. So it only accepts the input voltage 365 to 410 volt DC voltage, and it will step down to output voltage 12 volt. And then this output power is about 180 watt with target efficiency to be above 96% at full load. And you can also search this part number UCC25661 EVM128 in online, and you can search the block diagram and the key component used in the reference design. Okay. All right. So yeah. So that's end for my session. Yeah. Do you have any question regarding the charger, also BMS, or also traction inverter they want to clarify? Yep. Okay. Yep. Okay. If no, then I will end my session. So thanks everyone for attending today. So I will wrap it down now. Yeah. Thank you everyone.